Welcome back. Let us continue with the problem solving. In the previous lecture, we took some examples where the developed equations could be applied in solving some numerical problems. Let us now extend our discussion to another type of problem. The question is, calculate the standard molar entropy of N2 gas at 298 Kelvin from its rotational constant is given, B is equal to 1.9987 centimeter inverse, and its vibrational wave number is given. The problem that we discussed in the previous lecture was based upon moment of inertia. Okay, remember B is equal to H cross by 4 pi Ci. So, if I know moment of inertia, I can get the rotational constant. And towards the vibration side, there we talked about frequency. And here we are talking about the wave number. So, H nu is equal to Hc nu bar. So, these should be easily interconvertible. The question that we need to address here is the standard molar entropy of nitrogen gas. When I say standard molar, we are talking about the standard state. Standard states that we represent by the symbol this, and we put pressure here is equal to 1 bar, and molar means I will talk about Sm naught. This is what basically I mean. For the sake of simplification, I will not write M and naught, I will simply write S, but you take it as standard molar entropy. The question says that you calculate the standard molar entropy from the given values of rotational constants and vibrational wave number. So, therefore, we need to find out such a connection. Obviously, we need to connect entropy with the molecular partition function. So, we know that entropy is equal to U minus U0 by T plus K log Q, that we know. Now, since we are dealing with nitrogen gas, when you are dealing with nitrogen gas, the gas molecules are indistinguishable. When the molecules are indistinguishable, then canonical partition function is equal to q raised to the power n by n factorial. So, what I have now is S is equal to now U minus U0 by T plus K log q raised to the power n over n factorial, which is now I can write U minus U0 by T plus K log q raised to the power n minus K log n factorial. All right. Let me rewrite it. S is equal to U minus U0 by T plus Nk log Q minus K log n factorial is n log n minus n. Okay. Next, S is equal to U minus U0 by T, Nk is equal to Nr, we have discussed many times, log Q minus Nr log n plus Nr. Right? We are doing this K times N is equal to K, N is equal to N times Na, and K into Na is R, which is equal to Nr. This is what we have done. Let me write down this on the next slide. what I have is S is equal to U minus U0 by T, this is 1. Then we had nr log Q plus nr log Q minus nr log n minus nr log n plus nr. Now, we need to also connect this u minus u0 by t with the molecular partition function. And that also we know, u minus u0 is equal to minus n by q del q by del beta at constant volume, which I can write as minus n del log q del beta at constant volume. dq by q can be written as d log q. Now, sometimes it becomes easier if you differentiate with respect to temperature than when you differentiate with respect to beta. Beta is equal to 1 by kT. So, therefore, temperature derivative can also be done with respect to temperature, or it can be with respect to beta. Now, you consider d by dt, I write d by dt, I can write as d beta by dt into d by d beta. Mathematically that is allowed. And remember, beta is equal to 1 over kT. Therefore, d d beta, therefore, when you take its derivative, it will come minus 1 over kT square, this is d beta by dt, into d d beta. So, that means d d beta I can write as minus kT square d by dt. This is mathematically allowed. I will now use this information over here. That means now I have u minus u0 is equal to minus sign, and minus sign will go away. So, I will have it is square minus plus n k t square into del log q by del t at constant volume. What I have done is simply change the differentiation from d d beta to d dt. Now, let us substitute this information into this expression. What I have now, S is equal to u minus u naught by t. So, therefore, 1 t with t square, 1 t will get cancelled. So, I will have nkt del log q del v del t at constant volume plus nr log q minus nr log n plus nr. We have reached up to this. This t square becomes t because u minus u naught by t is used. Now, what I will do next is to make the things little easier, I will combine these two terms. Let us say, if I combine these two terms, I can write n times k del t log q del t at constant volume plus nr minus nr log n, right. This nk also I can write nr. So, therefore, now I will write S is equal to nr del t log q del T at constant volume plus nR minus nR log n. Let me write this. I hope this is clear to you that these two can be combined to write this derivative. If you open up this derivative, you will get this expression. For example, when you act upon del T log Q by del T, then it is derivative of A into B. So, T into del log Q by del T at constant volume, this first term, then plus log Q, this term, nR is anyway common. Let us write this expression on the next page for further solving. So, I have S is equal to nR del T log Q del T at constant volume plus nR minus nR log n. The given question is on nitrogen gas. Nitrogen gas is going to have translational degree of freedom, is going to have vibrational degree of freedom, is going to have rotational, all translational, rotational, vibrational degrees of freedom are there. So, therefore, I need to calculate the entropy due to translational contribution, rotational contribution, vibrational contribution. First of all, let us talk about translational. When I talk about translational, then Q translational is equal to V upon lambda Q. Lambda is equal to H upon root 2 pi m kT. So, that means this is equal to V upon lambda cube upon H cube 2 pi m kT raised to the power 3 by 2. This is what I am going to get, V upon lambda cube. We are asked to solve this at T equal to 298 Kelvin, 25 degrees centigrade, and we are given standard state conditions, right. I said I am not writing not, but assume that this is not. That means I can get V naught, V, P, V, M naught is equal to RT, where P is also P naught, which is 1 bar. By using this, you can get Vm naught equal to RT by P naught. Temperature is given, pressure is given, which is 1 bar. You can convert into atmosphere and use the appropriate units. This comes out to 24.78 liter, which is equal to 24.78 into 10 raised to the power minus 3 meter cube. When you actually substitute this QT into here, listen to me carefully. When you put this QT into here and write an expression for translational contribution, go back to Sackur tetrode equation. We have included n factorial factor and come up with this expression including nr minus nr log n. Therefore, this expression, when you apply for translational contribution, will eventually take the form of Sackur tetrode equation. And what is Sackur tetrode equation? nr log, I will write e raised to the power 5 by 2 2 pi m kt raised to the power 3 by 2 into V, I'll put Vm naught, right? I'm not writing standard state on that side, but consider this as a standard state. This is equal to, or I will have Na into h cube. I am not deriving this because we have derived it earlier. In fact, when you put Qt is equal to V by h cube 2 pi m kt raised to the power 3 by 2 here, in this expression, you are going to get this Sackur-Tetrode equation. We know the value of Vm naught, m we know for nitrogen, 28 divided by Avogadro constant into 10 raised to the power minus 3. We know Boltzmann constant, we know Planck's constant, we know Avogadro constant, and when you substitute the values, this is coming to be equal to 150.4 joules per Kelvin per mole. We have got now the translational contribution. We still have to get the rotational contribution and vibrational contribution. Let us now work towards obtaining rotational contribution. If we go back, or we can just take a look at this expression. For translational contribution, we have already included the n factorial expansion. Remember, we used q is equal to q raised to the power n by n factorial. Okay? This molecular partition function is the product of translational, rotational, vibrational, etc. But n factorial is not coming with each q. N factorial is coming only one. That we are including here along with the translational contribution. You can include with rotational also, vibrational or whatever, because this factor is going to come only once. We have included here in Sackur-Tetrode equation. Therefore, we need not use it when we discuss rotational contribution or we discuss vibrational contribution. Let us now switch over to rotational contribution. So, for rotational contribution, what I will do is I will use same thing nr del T log Q by del T constant volume, and I am not going to use the rest of the term because those have already been used with the translational contribution. Now, Q rotational is equal to 1 upon sigma h c beta b, that we know. I can write this as kt over sigma h c b. Beta is equal to 1 over kt. All right. So, what I will do now is I will substitute here SR is equal to NR into, let us see what do we get. If I keep T by Q del Q del T, this one will come plus log Q will come into del T by del T 1. This all is going to be at constant volume. Let us see what we get. T by Q. T by Q. Q is KT into sigma HCB into del Q by del T. When I take derivative of the partition function with respect to T, this is going to be K over sigma HCB. That's it. And plus log Q, this is the bracketed term, and you already have here NR. So, what I have now, SR is equal to NR into KT sigma HCB and KT sigma HCB cancel. So I have 1 plus log Q, where Q here is QR only. Or what I have, NR into log Q is what? Q is KT over sigma HCB. This is log Q plus 1. This is what I have. But remember that we are using the high temperature result, because we are using QR is equal to KT by sigma HCB, which is only possible if the temperature, rotational temperature, is higher than the actual temperature. So for that, what you will do is you will use K theta R is equal to HCB. Use this, you put in the value, you will get theta R equal to 2.87 Kelvin, right? And your given temperature is equal to 298 Kelvin, which is much higher than 2.87 Kelvin. So therefore it is justified to use QR is equal to KT over sigma HCB. Now you substitute the values and what you will get is 41.14 joules per Kelvin per mole. K is Boltzmann constant, T is the temperature which is given to you, sigma is equal to, in this case it is a nitrogen, so therefore sigma is equal to 2, and H is Planck's constant, C is speed of light, and B is the rotational constant. We have done for rotational contribution also, and now let us talk about the vibrational contribution. So SV is equal to NR del T log Q, Q here is QV over del T at constant volume. So what I have now is, let us do it. Q vibrational is 1 over 1 minus exponential minus Hc nu bar by Kt. I am writing in terms of temperature. Therefore, my SV becomes NR. It will be easier if I talk in terms of log Q. I am not writing V here for simplicity. So this is minus log 1 minus exponential minus Hc nu bar by Kt. This is what I have. Now let us take the step forward and expand this differentiation. What I have now, T into derivative of log Q, derivative of this, which is going to be minus 1 divided by 1 minus exponential minus Hc nu bar by Kt into minus exponential minus Hc nu bar by Kt into next derivative is equal to Hc nu bar by Kt square with a plus sign. This is what will come. Then plus log QV. Let us combine now. S is equal to what it will come? NR into hc nu bar by kT, that is coming from this term and this term, and then I have into exponential minus hc nu bar by kT divided by 1 minus exponential minus hc nu bar by kT, and log q we already have, it is minus log 1 minus exponential minus hc nu bar by kT. Right, quite complicated term. Substitute the value hc nu bar by kT. All numbers are given to you, nu bar is given to you. When you calculate, this comes to 11.38. And when you use this into this expression, what you will find that SV, vibrational contribution, is nearly 0, approximately 0. Numbers are going to be very small. So now we have S total, let's say. This will be S translational plus S rotational plus S vibrational. We have S total is equal to S translational was 150.4, S rotational was 41.14, and this was 0. So many joules per Kelvin per mole. So therefore your entropy comes out to 191.54 joules per Kelvin per mole. Quite a lengthy numerical problem, but at least it discusses how the different contributions must enter in when you evaluate the overall thermodynamic quantity. Here we have shown for the case of entropy. But suppose if the question is for Gibbs function or for Helmholtz function or enthalpy, then you must include the translational contribution, rotational contribution, or vibrational contribution, whichever mode of motion is fully active. In this particular case, you noticed that there is a sizable number coming up from translational contribution and rotational contribution, and vibrational contribution was nearly 0. So I hope that this particular example has brought in clarity on how to calculate a thermodynamic quantity from the molecular partition function, which has different contributions such as translational, rotational, vibrational, and if the temperature is so high, then the electronic. We will discuss a few more problems, but in the next lecture. Thank you very much.